Okay, we're back. And what I was just about to get to was the caveat, that is the catch. We've been using these equations for static and kinetic friction, and it should just be noted that these equations are empirical. What that means is derived from experiment and not rather than from theory. And so there are a lot of cases where they don't really work. They're useful in some cases, but you have to be careful in using them. They're not universally applicable, and in many cases, they at best will give you a good approximation of what the forces might be. There are also a lot of experimental details that can affect the coefficients of static and kinetic friction. For instance, like the type of wood. If you're looking up using the coefficient of friction for wood on concrete, what type of wood is it? Is it oak or is it pine? That might make a difference. Pine is softer, so it might dig in more on the floor. Is the wood rough or is it smooth? Has it been sanded? Are you pushing with the grain or across the grain? That could have an effect too. As for the concrete, is the concrete, how smooth is it? Is it textured? Is it broken in any places? Are there rough spots? All of that can have an effect. So we generally consider these equations to be approximations at best. Also, the equations don't work if the surfaces have been lubricated, and the equations tend to break down at high speeds. So fortunately, we're sticking to examples at basically low speeds, no oil or anything anywhere in sight. So to continue with the examples, the next one is 20 kilogram crate that's at rest on a floor. The coefficient of static friction is 0.7, and the coefficient of kinetic friction is 0.6. There's a horizontal force P that, a vector force that is applied to create, to the crate. And we want to find the force of friction if, P equals 20 newtons, or P equals 30 newtons, or P equals 120 newtons, or P equals 180 newtons, depending on how hard you're pushing the crate. Presumably P stands for push. Before we can actually do this, we have to find out whether to use the coefficient of kinetic friction or the coefficient of static friction in each case. In other words, how much force will cause the crate to move? So that's the first thing we do. We know that Fs max equals mu sub s times n. N in this case is equal in magnitude to the weight, which is mass times gravity. So that's 20 kilograms times 9.8 meters per second squared. That's 196 newtons. And mu sub s is 0.7. So when we figure out what Fs max is, it's 137.2. So what that means is that if P, the pushing force, is greater than 137.2 newtons, the crate will be moving, and you should use mu sub k. If P is less than 137.2 newtons, the crate will be sitting still, and the actual force of static friction will be equal to, in magnitude anyway, to the pushing force. Okay. So let's see what we're given here. P equals 20 newtons. 20 newtons is less than 137.2, so the crate is stationary. Fs max we saw was 137 0.2 newtons actually. The actual Fs, that is the actual force of static friction, will be equal to the pushing force, which is 20 newtons. Okay, if pushing force is equal to 30 newtons, again, 30 newtons is less than 137 newtons. So the Fs actual, that is the actual force of static friction, will be equal in magnitude to P, which is 30 newtons. For part C, they've upped it to 120 newtons of pushing force, but that's still less than 137. So the actual force of static friction is the same as the magnitude of the pushing force, which is 120 newtons. But for part D, they've upped it to 180 newtons. 180 newtons is greater than 137 newtons. So the crate is in motion, and we have to figure out what the force of kinetic friction is using mu sub k. So the force of kinetic friction is mu sub k times the normal force. That's 0.6 times 196 newtons, or 117.6 newtons. And I don't believe they actually asked for it, but if you're interested, the acceleration of the crate when it first starts moving will just be the net force over m, the mass, because F equals ma. So A equals F over m. The net force, though, is 180 minus 117.6 newtons, because remember, you're pushing forward with 180 newtons of force, but the crate is pushing backwards with 117.6 newtons. Okay, so that's the net force, 180 minus 117.6 over the mass, and that gives you 3.12 meters per second squared. So that would be your acceleration when the crate first starts moving. Okay. There's also the question of friction on inclined surfaces, like say a box on a ramp or a skier on a hill. And in case of sloping surfaces, we generally treat those as inclined planes. We assume them to be flat, but not necessarily smooth. If we're given the materials that the surfaces are made of, we can look up a coefficient of friction, or if we're given a coefficient of friction, then we would need to use that in our calculations. In the example of a skier going downhill, we have a skier with a mass of 62 kilograms who is descending a snowy slope at a constant velocity. And what we want to do is find the coefficient of kinetic friction if the force of friction is equal to 45 newtons. Okay, so looking at the situation here, oh, they didn't mention in the text, but the diagram shows that the angle of the hill is 25 degrees to the horizontal. So you've got the skier, and you've got the skier's weight, which is pushing straight down toward the center of the earth and is therefore not perpendicular to the slope. And from the weight, we can find the X and Y components. We're going to use a system where the X-axis is parallel to the slope and the Y-axis is perpendicular to that. So through the equations that we will see in a minute, we can find the X component of the weight. That's the component of the weight that pulls the skier down the hill. And the Y component of the weight, which is what is balanced out by the normal force, which is perpendicular to the slope. And then you have the frictional force pushing backwards on the skier. It's a little clearer to see in a free body diagram where the dot is the skier, and you have the X component of the weight pulling the skier down the slope, frictional force pulling the skier back up the slope, and the Y component of the weight, which is balanced by the normal force. Okay, in this case, we know that the force of kinetic friction is equal to the coefficient of static friction times the normal force, but we don't know the normal force. The normal force, though, should be equal in magnitude to the Y component of the weight. Okay. opposite in direction, but equal in magnitude. So normal force in terms of magnitude, notice there's no vector symbol above this. So we're just talking about the magnitude of the normal force is equal to the magnitude of the weight, which is equal to mg on level ground. But on an incline, the normal force would be equal to the y component of the weight, which is equal to the magnitude of the weight times the cosine of the angle, which in this case is 25 degrees. The magnitude of the weight is just mass times gravity times cosine 25 degrees. So this is going to be 62 kilograms times 9.8 meters per second squared times the cosine of 25. That gives us a normal force of 550.7 newtons. All right, since the force of kinetic friction equals mu sub k times n, we can just rearrange this equation to solve for mu sub k, or the coefficient of kinetic friction, which will be the force of kinetic friction over the normal force. And that's going to, they told us in the problem that the frictional force was 45 newtons. Since the skier is moving, that must be the force of kinetic friction. So that's F sub k over n, the normal force, which we just found, 550.7. And that gives us a coefficient of kinetic friction of 0.0817. Okay, this leads us to a general equation that we used in this equation. On an incline, the force of kinetic friction is always equal to the coefficient of kinetic friction times mg cosine theta. That equation is general. You can use it on any slope. Also, on any incline, the coefficient of kinetic friction is equal to mg sine theta over mg cosine theta. The mg's cancel out, of course, and sine over cosine is equal to tangent. So actually, the coefficient of kinetic friction is equal to the tangent of theta. That's if the object is moving at a constant speed, though. But you can use this on any incline as long as there's no acceleration involved. And if you take the tangent of 25 degrees, which is the angle of the hill in this case, you get 0.466, which is not, which is actually not the value we got in this case. So what's going on here? Okay, so never mind about that. What we got here should be correct. I'm not sure why that didn't work. Well, that'll teach me. All right, so the atomic, let's see, moving on, the atomic scale origins of friction is something that I kind of already talked about. So just as a quick review, not only is friction due to the roughness of the surface, but it can also be due to the chemical composition of the surfaces that are in contact with each other. So the more strongly attracted the chemical substances are, the more friction you're going to get. Okay, in this example, example 12, we've got some sliding blocks. And got two blocks that are attached to each other by a cord, which is weightless, through a pulley, which is assumed to be frictionless. And one box is on top of the other. And the top box has a mass of 2 kilograms, and the bottom box has a mass of 4 kilograms. And what's happening is there's a force, which we'll call P, pulling, presumably that's what P stands for, on the bottom heavier box toward the left. And that's going to have the effect of pulling the lighter box well, it's going to have the effect, first of all, of pulling the heavier box toward the left, of course, but it's also going to have the effect of pulling the lighter box to the right across the bottom box because of the way they're attached on the pulleys. If you pull the bottom box to the left, that's going to pull on the string, which is going to pull the top box in the opposite direction. Okay. So we want to know, what is the magnitude of the force required to move the blocks at a constant speed? And we can assume that all of the coefficients of kinetic friction are equal to 0.4. So that would be the box against the floor and the box against the other box. They would both be 0.4. So for the top box, the 2 kilogram box, we've got a diagram that looks like this. We've got the weight of the top box pulling downward. And that's going to be 19.6 newtons. That's what you get when you take 2 kilograms times 9.8 meters per second squared. That's 19.6 newtons. You've got the normal force pushing upwards on that box. And you've also got, let's see, the force of friction, which is pulling to the left on the top box because the tension in the line is pulling the top box to the right. So friction pushes, the other way. And this friction, which they're calling F1 for friction of box number 1, would just be equal to the coefficient of static or kinetic friction times the normal force for box 1, which is 19.6 newtons. For box 2, you have an even more complicated situation. First of all, you got the normal force of box 1 and the normal force of box 2, and you've got the pulling force pulling to the left, but pulling to the right, you have the friction of box 1 and also the friction of box 2 and the tension in the line, all pushing or pulling against the pulling force. Okay, so we can consider the motions of the blocks separately. That would be the easier thing to do. On the top box, we've got the contact force from the bottom block. That's 0.4 times the normal force of box 1. And N1, that is the normal force of box 1. Those are the components. The tension, we have the tension in the string, which we'll call the tension for box 1, even though the tension should be the same throughout the entire string. And we also have the weight of the top block, which is mg, or in other words, 19.6 newtons. For the bottom block, we have the contact forces from the top block and the floor. For the top block, we have the components that are negative of the normal force for block 1 and 0.4 times the normal force for block 1. And those are reaction forces to the contact forces of the bottom block on the top block. And for the floor, we have the components are N2 and 0.4 times N2. That is the normal force for block 2. That is the Y term. And the X term is 0.4 times N2 because that is the force of friction. Okay, just as this up here was the force of friction of box 1. Okay. We also have the pulling force. That's a force in the X direction. We have the tension in the line, which is a force in the X direction also. We have the weight of the bottom block. That's in the Y direction. That's going to be negative mg, or in other words, negative 39.2 newtons. since the top block is moving to the right at a constant velocity, because our original question said, what is the magnitude of force for P, that is the pulling force, that's required to move the blocks at a constant speed? Okay, so we know that the top block must be moving to the right at a constant velocity, and the bottom block must be moving to the left, also at a constant velocity. For the top block, you can sum up all the forces in the x direction, which should be equal to the mass of block 1 times acceleration in the x direction, while the summation of all of the forces on block 1 in the x direction would be the tension in the string minus F1, which is 0.4 times the normal force for block 1, and that equals 0. And that's because the box is moving at constant speed. Okay, so we have T minus 0.4 N1 equals 0. What that tells you is that T must be equal to 0.4 times N1. And we don't know what either of those is yet, but we can find out maybe something over here that will help us. If we add up all of the forces in the y direction on the top box, we have that being equal to the mass of box 1 times acceleration in the y direction. The summation of all of the forces in the y direction of box 1 would be the normal force for box 1 minus the weight, which is 19.6 newtons. And that has to equal 0 because it's moving at constant speed. So there's no acceleration. Acceleration is 0. And so in other words, what we see here is that N1 must be 19.6 newtons, which makes sense. And you can then take that value, N1 equals 19.6 newtons, and stick it in over here. So tension equals 0.4 times N1, which is 0.4 times 19.6, or 7.84 newtons. That's the tension in the line. All right. That is one of the things we need to find the ultimately the magnitude of the pushing or pulling force in this case. To find that, we have to go look at the bottom block. It's also moving at a constant velocity in the x and the y direction. That is constant velocity moving in a constant velocity in the x direction. The constant velocity in the y direction is 0. And that means there's no acceleration in either the x or the y direction. And so you can look at the x and y direction for block 1. The sum of all the forces in the x direction should be equal to m2, that is the mass of block 2, times its acceleration in the x direction, which is 0. The sum of all the forces in the x direction on the bottom block should be the tension in the string minus the pulling force plus, or in other words, minus a negative, 0.4 N1 plus 0.4 N2. Okay, looking at what we know, the tension is 7.84 newtons, which we found out above. N1 is 19.6 newtons, which we found out above. N2, we don't know, which is why we're going to go over here and try to find N2. If we sum up all of the forces in the y direction on the bottom box, that should be equal to the mass of the bottom box times its acceleration in the y direction. And that should be equal to 0 because, again, it's not accelerating in the y direction. So A equals 0. And therefore, m times A equals 0. The forces on the y box, or the forces on the bottom box in the y direction, should be the normal force on the second box minus the weight of the bottom box, which is 39.2 newtons, minus the normal force of box 1, which we know from over here is 19.6 newtons. So N2 minus 39.2 minus 19.6 equals 0. And therefore we can solve for N2. N2 must be 39 plus N 39.2 plus N1, which is 39.2 plus 19.6, which is 58.8. All right, so now knowing that N2 is 58.8, we can come back over here and put it in here. So T, which is 7.48, plus 0.4 times N1, which is 19.6, plus 0.4 times N2, which is 58.8, equals P. Add all of that up, and P is 39.2 newtons. Okay, that was a bit of a long one, and that's going to require some reviewing probably to sort of figure out how that was done. But feel free to review the video as many times as you need, as that was a fairly complicated one, and that is definitely enough for this segment of the video. So I will leave it there, and we'll pick it up here next time.